Right, so we've talked a little bit about contaminant transport. We made the case early on, I think, that our discussion of this would be divided into two parts. One in terms of conservative transport, which is what we've talked about so far, which means basically that anything that gets dissolved and ends up as an aqueous component stays in solution, doesn't get sorbed onto any of the solid material. And we talked about understanding the two basic mechanisms by which it can be transported. Of course, if these plugs, chimneys of free product that are stuck by capillary forces did not dissolve, of course, it'd be a non-problem, right? Because it would just stay in place. It wouldn't end up in the drinking water downstream because physically it couldn't be transported there. So it's really just the agents of transport that we are interested in worrying about. And those come in two flavors. One is advection, where it physically gets carried from point A to B on the backs of the water, on the back of the water that's traveling downstream. And at the same time, it on that background, as it traverses from one location to another, it is able to spread by one of two mechanisms. The first and the slowest is by molecular diffusion, which is just Brownian motion, the same as putting ink in water or ink in milk, as we've talked about. And another mechanism, which is mechanical mixing, hydrodynamic dispersion, which looks just like the behavior we get from diffusion. It's this Gaussian cloud that starts like a skyscraper and gets progressively wider and wider, but it's because it gets mixed by the tortuous flow paths that it takes and the non-uniform distribution of velocities in pore throats and fractures, etc. And so those are the components we've talked about so far, all so far applied to transport of conservative species, ones which aren't ultimately sorbed. So that's kind of where we are. We defined an expression that describes that behavior, and that's the advection dispersion equation. I don't think we need to belabor the use of it as an equation, other than the fact that it allows us to be able to represent some different behaviors, and those behaviors, if you like, are epitomized by this little cartoon here. In terms of an upstream concentration, giving something in terms of what it looks like downstream. Okay, did I not put something in? Did I open it up in the wrong? That is very curious. Does it not like it on that screen? It's kind of curious. Let me try this. I don't know if it's because of that. I can't imagine that would be the case, but that's all I can think of. Get there. I didn't. All right. And then you're gone there. All right. And let's try it. Actually, it's out of. Yeah, I kind of doubt that it's that, but it may be. No, does this not work? It's plugged in. Okay, just. All right, we'll cut that out of the movie. But anyway, so the behavior is in terms of these little cartoons, which represent behaviors for plug flow. If we have this step increase in concentration at the upstream, then a plug moves down through it, 100% concentration behind it, 0% in front of it at any particular time. And we can also get the residence time distributions at the bottom side, which would be something like this for step flow, and for diffusive flow, it would be spread. All of your work, so you can also apply it to kind of a pulse, a spike behavior, when you get this spike moving downstream, and depending on dispersion, as you get dispersion in the system, it gets flatter and flatter and wider as a result of that. And so last time we used this advection dispersion equation to be able to say something in terms of exactly what this residence time distribution would look like at the downstream portion, and to actually quantify it. And we spent some time defining exactly how that works. And that was our main activity last time. So that's kind of where we are. We have some expressions that allow us to say exactly what's going on in the system. And we know that the main property, if you like, that defines this behavior is some magnitude of dispersion coefficient, which is something like this. A coefficient times an advective velocity in the longitudinal direction plus an effective diffusion coefficient. So we've used that terminology throughout. And so this left-hand side is the mechanical effect by going in and out of the pores. The right-hand term is just Brownian motion, diffusion, by putting fluid in a beaker, which maybe happens to have sand in it, and so it can only diffuse in the tortuous flow path, although the fluid is stagnant within that. And so if we want to be able to understand how contaminants are transported in the subsurface, we perhaps need to say something about figuring out exactly what these coefficients might be, how we might measure them. Because presumably, if we're able to measure them, then we can do something useful, as we alluded to last time. If you measure what a plume might look like at some particular time, and you can say what it is, then you might like to be able to say exactly what it would look like 20, 100, 300, 3 years later, 300 days, 3 years later. To be able to do this, we need to be able to define exactly what the material properties are. So I suppose, without giving anything away for assignments, key properties that would figure into this would be advective velocities. I suppose it would be the time since the release occurred and the advective velocity. And it would be all the components that go up to make up these ensemble dispersion characteristics. So the overall behavior is defined in terms of this, but this in sequence is defined in terms of component parts, which are a dispersivity, I think is the name. It's units of length, an advective velocity in the longitudinal direction, and a diffusion coefficient. All of these units are in length squared over time. And so if we know what this is by somehow looking at the current state, then we might be able to predict what it is going to be in 3 years' time. That's basically our issue. And so these expressions that we've developed to describe exactly how this plume evolves, we could use to look at the behavior at some time that you measure it, and then project it to be able to look at this. So that's basically our desire. And so you could imagine that would come in a variety of different ways. We could measure something in the laboratory to do that. We could measure something in situ to do that, where we do some kind of in situ experiment to perturb the system and measure its response. Or we could just look at natural systems as they evolve, or a given site as it's evolved over its time since the spill occurred, and now time 10 years later, to be able to figure out what those properties are. So each of these, we'd like to be able to figure out what this dispersion coefficient would be. That's our ultimate goal. And so we'll look at a variety of those 3 different ways. That's all we'll do today, what we'll talk about. I won't talk about that. I don't think it's relevant. And so the relevance of this, I suppose, is to understand behaviors in terms of what would evolve. So this happens to be a chloride plume. It's relative to a landfill, refuse pile, somewhere in southwestern Ontario, as it turns out. It's in Fetter's book. And this stuff has been leaching into the groundwater over time, maybe lined, not lined, I'm not sure. And there's some flow regime which presumably, if these are the contours of chloride concentrations, then you don't have to look very long at this to be able to figure out it must be flowing from left to right, because all the transport of this is with the transport of the fluid. So diffusion, if it was diffusive only, you could imagine, I suppose, that the plume might look like this because it's going in each of these directions. But if it has this big component which is in the rightmost direction, then you could pretty much conclude that it's, if not advection dominated, it at least has a significant component of advection that's carrying it down gradient. I suppose you could surmise that as well if you look at the water table. the water table has a slight gradient to it towards the, I guess the gradient is positive towards the left. Yeah, your left as well. But it's sloping down, so if you use Darcy's law, it would suggest that there's some velocity towards the right. And so depending on the magnitudes of the coefficients which describe this behavior, if you try and represent by modeling this plume and how it would evolve from some input from the source as a function, a continuous input of the source as a function of time, then depending on the magnitudes of the properties that you assign to it, and I'll blow it up so you can perhaps see this, that these are indeed the magnitudes of these transport properties. And so presumably defined by this is if there's a gradient here, then you'd expect that the advective velocity is some function of hydraulic conductivity over porosity times gradient. The gradient is defined by this, so that's kind of given. If you, for instance, have well bores or wells upstream and downstream, and you measure the water level difference between them, that immediately gives you at least some kind of reference gradient to be able to apply. If you know something about the permeability or hydraulic conductivity, I guess in this case, and also the porosity, then that defines an advective velocity that goes from right to left. If that defines an advective velocity, then we also know that the longitudinal dispersion is a function both of a longitudinal dispersivity coefficient and this advective velocity, and also some magnitude of this effective diffusion part. Because the plume is so definitively lopsided, you might surmise from this that this is big and therefore relatively big and gives this left-hand term a larger influence than this. Otherwise, diffusion would occur equally in all directions. So that's the first clue. And so the scaling parameter here is some magnitude of this longitudinal dispersivity. In each of these cases, this is all put at the same amount. We'll talk about how we might choose this interesting magnitude. It's just a length in this particular case. And all that's changed in these individual cases is that the value of this transverse dispersivity is a relatively larger number, a smaller number, and an even smaller number. And so the actual model that's used, I guess physically what would happen as a result of this is that if you can imagine that this says something about how spreading will occur in the transverse direction, right? And so if you have this section, it's a two-dimensional section of a three-dimensional problem. If you looked in plan view at what this plume might look like, if I kind of just draw it down from here, and so this is the refuse pile that's sitting here, then you can imagine that it might look like a little bit like this in plan view, that it's getting pulled downstream because of the advective velocity. And so if you represent this in some way, the magnitude of this lateral dispersion coefficient, d sub L, would control how widely it would spread. If you thought, for instance, the value of this was 0, then I suppose you might assume that really the distribution of the contaminant, you could think of it as just being held between two walls, can't disperse to the side transversely. I want to write that not as L, but transverse. I'm thinking lateral, so it's longitudinal we've used for L and T for transverse. So if you restrain it from doing that by having these barriers here, which is exactly what would happen if this transverse dispersion goes to 0, then you'd think that you trap all of the stuff that's being carried from here in this between these two walls. And you'd expect as a result of that, that the concentrations that you'd get would be affected by that. And not surprisingly, if you trap all of it between those two walls, you'd expect that the concentrations in here would be much larger than if you allow them to spread much further outside. And so choice of both of these parameters will condition, in this case changing only one of them, will condition this distribution of concentrations within the system. And so our choice of those parameters is something that's perhaps important for us to be able to do. And so that's what we'll look at. And so you can imagine there's these three primary ways of doing it. And we'll talk in broad terms about each of them. Laboratory measurements, field measurements where you force flow to occur, and field measurements where you just allow flow to occur at the natural gradients. And so the first one is laboratory experiments. You'd think that that would be useful because you could take samples out of the field, you take them back to the lab, and then you do experiments on those samples. And the experiments that you do, you could imagine, would be just the same as what we've talked about in terms of our calculations of transport downstream, is that you would turn on a concentration magnitude at an upstream face at time t0, so that the boundary condition at that upstream face would look like this with time. This would be C over C0. And you'd hold it on for all time. At a particular snapshot in time, the plume within the core would look either like the behavior for plug flow, or if it was dispersing, it would look like this. And you couldn't really see this because you can't see into the core unless you did it in some kind of transparent box with transparent beads, which I guess you could do, but typically is not. But you can look at its arrival at the downstream face. And if you plot the arrival at the downstream face, then this plug flow translates to a residence time distribution that looks like this. In a conservative tracer, this time would be equal to, I guess, length over velocity. Is that right? This is length over time, and this is length. Yeah, so I think that's right. And we could use our expressions that we've talked about before in your assignments to be able to do that. And if there is dispersion, then we could use this distribution for whatever the arrival time curve is. So in other words, this would also be one pore volume. And what we talked about last time was this T sub R was equal to 1. That's basically one pore volume. In other words, the fluid that you put in the upstream end has traveled downstream at one pore volume. It immediately, or is incipiently about to break through on the downstream side and exit. And so we'd expect that to be the case. If there is spreading, then that means that sometime before one pore volume, then we actually see concentrations that were larger than 0, which they wouldn't be otherwise. And so that's really inferred here. So presumably what we could do is we could take those relationships that we plotted up last time to look at the distribution of the breakthroughs, which were shown, I guess I'm going back a long time, but these expressions here. We know that Peclet number equals infinity would be this one. So this is Peclet number, which is what? Advective velocity times the length of the core divided by dispersion coefficient. Infinity in this particular case. And as it gets progressively smaller, 100 we said, 10, and 1, I think, in this case. They no longer pass through this kind of fiducial point of the coordinates of this are relative concentration. Oops, let me draw it out here. The coordinates of this point are, importantly, relative concentration C over C0 equals 0.5, and pore volumes are equal to 1. And so for Peclet number of 100 and larger, they kind of go through this point. Once it's 10, then it's not quite going through this point. Once it's 1, then it really isn't going through this point. The 50% concentration arrives really early, at 0.4 of pore volumes, for instance. And so what you could imagine doing is you could take your laboratory data and you'd plot it in terms of these terms. And if it happens to plot on this particular curve, then you know that that corresponds to a Peclet number of 1. And if the Peclet number of 1, you know that the Peclet number is an advective velocity, the length of your core, and a dispersion magnitude. And so your measurements show where it lies. You know the length of the core, and if you know the advective velocity, just by measuring, I suppose you could measure, how would you do it? Well, you do it just from Darcy's law, but I suppose you could also do it from just the number of pore volumes. So in other words, this is the time taken for one pore volume divided by length of the core would equal the advective velocity, right? So put it in upstream, you know what the volume of your core is, you multiply the volume of your core by porosity, so you know the volume of the pore space. Once that amount of fluid has come out the other end of the core, because it's displacing old fluid, right, as new fluid comes through, that means one pore volume's gone through. If you know it takes 1 hour, then it takes 1 hour to go 10 centimeters. You have an advective velocity directly from that. And so you have there everything you need to do to be able to come up with this one parameter here. We know that this parameter here is dl, which is equal to this coefficient times advective velocity plus diffusion coefficient. We know that this number is something of the order of 10 to the minus 9 meters squared per second, just normal diffusion magnitudes multiplied by some number. Remember we talked about a tortuosity term, which could be a factor. We said it was between a half and 100, a hundredth. So it could be 10 to the minus 9, or it could be 10 to the minus 11 at the smallest. And so depending on the magnitudes of these, this is probably going to be trivial. If this big number is big enough, you can probably assume that this is not to worry about. You have this from the experiment, you know this, and therefore you can calculate this dispersion coefficient. And so in an ideal world, it seems that we can come up with one of these properties. We'd like to know this property, but we realize that this property is only applicable for one particular advective velocity. So I suppose you could do it as was done in these classic experiments here. You do the experiment at a variety of different velocities. And if you do it at a variety of different velocities, you get magnitudes of this transverse or longitudinal, just use longitudinal, magnitudes of this longitudinal dispersion coefficient that change from a number which is close to 1 to a number that varies linearly with velocity. And so it fits directly in here in that the regime where this is the largest number compared to this, in other words, velocities are so small that this term is nothing, is over here. There's a regime where this term is almost nothing because velocities are now big over here, and you'd expect to see a constant magnitude here, and a linearly increasing magnitude here would give this one-to-one slope of this curve and some transition in between. And so each of these dots here are determined in exactly the same way we talked about on using a core just 10 minutes over the last 10 minutes. Basically that experiment. And so it allows us to be able to come up with a magnitude of this parameter. And if we know what this parameter is and we know what the advective velocity is because we're prescribing it in our experiment, then we can say something about this maybe independent material property, which allows us to make this independent of velocity. So that's our goal. So having said that, and given the long argument over how we might do that, it might seem surprising for me now to tell you that we would almost never do that. And the reason we'd almost never do that is because one of the mechanisms by which this dispersion occurs in the field is by the fact that, again, actually I just saw a useful figure, this figure here. We've drawn this a couple of times. And the idea is this, whoops. If you think of an aquifer that has some stringers in it that happen to be higher permeability channels, these little dotted parts here, then you can imagine if you have a plume that's merrily going downstream from this pulse injection, it's talked about in the context of this kind of cloud going downstream, then you'd expect that if it has this chance to go on this highway that gives much larger velocities here than on either side of it, then you'd get it to spread out more. And so one of the mechanisms by which it spreads out in fingers is by the fact that it finds these much faster pathways to travel on. And so if you take a sample in the field that to scale maybe is only this big, compared to the structure of these high permeability pathways being this size, then you're only sampling something that really doesn't include the mechanism by which this thing spreads out. And so the reality is that when you look at dispersion, then taking a small sample and doing an experiment that we have just talked about would give you the parameters for that small sample. But if the plume, instead of being of the orders of sizes of centimeters, is meters or tens of meters or kilometers in size, then the appropriate size to do that experiment on is a sample that is that big. And clearly that's not captured in something that's basically the size of your fist. And so, although we can make the case that we can do these experiments, almost they're never done because they're almost never relevant to work at field scale. Okay, so could do it if you wanted to, but it may be an exercise in futility. So, if we know then that part of this big, large-scale structure of aquifer is going to be important, so the next logical thing then to say is, well, we could do some field experiments. And so field experiments would be just like, hopefully you learned in 452 that you drill a well, you start sucking water out of the well, and you look at, from a prescribed rate at which you pull it out, you have another well some distance away from it, and you look at the rate at which the water level is drawn down in that other well. And from that drawdown rate, you can fit that response to be able to figure out exactly what the appropriate permeability would be to that system. And so really what you're doing is you're exercising the aquifer by pulling water out, seeing how quickly it responds, and from the rapidity of that response, by fitting it to a model, you can say what the permeability is because you have a PDE that you're solving. Same for the equations for flow. So you want to exercise, or for transport rather, you want to exercise your aquifer by doing something to it. So you could imagine that an appropriate experiment would be to basically, sometimes called a huff and puff test or a push-pull test, but the basic idea is this. You take some salty water, you pump it into a well so it goes out from the well bore into the aquifer some distance. Not only the water goes out, but also the salt that's carried in that water. It gets to some radius. And so a picture of this might look like this. So after some time of pumping in, the front of the water that you've pushed in would be at this location. I suppose if you looked at the profile in a radius, and you looked at the concentration versus radius, then this is as far as the water has gone in a given time, basically one pore volume. So this is kind of the front at time TR, or one pore volume, 1 PV. Right? And so if it was plug flow exactly, then you'd expect the concentration profile to look, I suppose, like this. Right? The concentration would have gone as far as the front of the water has gone and no further. Conversely, if it's dispersive as it goes in, then the front might look like this. Right? So this would be dl equals 0. This is dl not equals 0. And so that's fine, but you have nothing to measure there. I suppose if you had a well at this location and you could measure concentrations at that well, then you might be able to do it. The alternative now is to reverse the flow. So you've pumped it in for one pore volume, maybe you pump it out for one pore volume. And then you look as it comes out as to what the residence time distribution would look like. And so what can we guess what that would look like? Well, it would be concentration versus time. So I suppose if you start off at time 0 when you're pumping in, and then this would be one pore volume. So if you monitor the concentration at the well bore while you're pumping it in at 100% concentration, I suppose this would be your initial concentration in, right? It wouldn't deviate from that. But now you reverse flow and you pull it back. I'm just going to keep on, I'm not going to reverse flow. So this is one pore volume, this is in. Now this is out. So what would it look like? Well, you'd still be pumping this stuff here initially at the early times. Then you'd be sucking this stuff out here at early times. And then you'd be sucking this stuff out here at early times. So I suppose if there was no dispersion, then you'd end up at this point here. And this would be two pore volumes, I would think. And then it would go flat. It would be zero. If the converse was the case, I guess if you're going along here, you'd bring out stuff which was not only reduced in concentration from when you put it in, but it also spread out and mix as it comes back in. And so you'd end up measuring something that I guess looks like this. So I'm do a big one over here. So this would be for dispersion not equal to zero. And this would be for dispersion equals to zero. So you get the idea. And so there's some expression that you could come up with for that. And so that seems like a potential, right? Because now no longer are we doing something on a sample that's this size, but we're doing something on a sample that maybe is as far as you can pump in a day and pump out another day or a couple of hours. So it might be tens of cubic meters of aquifer, perhaps. And so and we can use some expression to be able to represent that. It doesn't matter what that expression is. And it doesn't really matter what the expression is because it's not so useful. And the reason for that is that the dispersion characteristics are highly sensitive to the magnitudes of the velocities that we induce. And so because we're injecting fluid at some prescribed advective velocity, which is typically much higher than happens in the natural case in the field, is that the dispersion that we would get would be dominated by mechanical effects and it wouldn't necessarily reflect the true behaviors. And so even though we're doing it on a much larger volume and affecting a much larger volume of the aquifer, it might not actually be very useful for us for that. And so that's another drawback. So it satisfies one of our requirements as being a sample size that's useful to us, but it is not so useful because it's not actually at the gradients that we'd see happening in situ. There's also another feature, but I won't mention that now. I'll mention it in another experiment, which again is an experiment that over time has been shown not to be so useful. And one way to be able to do this is maybe not to use a single well, but in the same way as we talked about, you could imagine doing this previous experiment where instead of this being a core that may be 2 inches or 5 centimeters long, maybe this could be a core which is 500 meters long. And not that you'd sample that, but if you had that in the field, by looking at pumping in something at one end, recovering something at the other end, and having it over a very long length so it's actually representative of your fuel aquifer, then you'd think there would have some representation of the fact that you might have these lenses that would be the fast channels or the fast transporters, and therefore the dispersion that you'd measure would be representative of the large-scale behavior. And so it's not very easy to do that. Actually, some people have done that. Some people have worked in, perhaps we'll talk about in site investigation, digging a trench upstream, a trench downstream, maybe 5 centimeters apart, increasing the gradient slightly upstream, decreasing it downstream, putting tracer in the big trench upstream and allowing it to flow from one side to the other, and looking at the residence time distribution as it arrives downstream. But the other way to do this, if you're not doing that, say if you wanted to be at 20 meters depth or 50 meters depth or 100 meters depth or a kilometer's depth, is to do it by using wells. And so you could imagine doing a tracer test with wells, and this kind of highlights one of the fallacies of this injection recovery test that we just talked about, or the push-pull test that we just talked about. And that is that there is some mechanical dispersion that occurs, which is purely a function of the geometry of the test. And you can see it here, that if you think about injecting fluid here and recovering fluid here, so this is just a plan view of two wells, one that goes in here and one that goes in here. You inject water with some salt or some tracer in it from the upstream, and it travels to the downstream locations. These blue curves, which I'm overwriting, would be flow lines. So this is just a potential flow net, which again you should also have dealt with in 452. The lines that cross those perpendicular are equipotentials. And what we know is that if the potential, basically this says if the value of the head here is equal to 10, 7, 6, 5, 4, 3, and the value of the head here is equal to 3 meters, so it has units, then the potential at each of these other intermediate locations, this would be 9, 8, 7, 6, 5, 4, and 3. And so the drop in head between each of these locations is the same. And so since we know that advective velocity is equal to hydraulic conductivity, porosity, and head gradient, then if the head gradients get smaller, when these other two parameters as material properties stay the same, then this is going to go down. And so if you look here, this head gradient here has to be larger than the one here. They drop by the same amount as they go from upstream to downstream, but it occurs over a larger length dl, dx I guess we call it, versus this dx. And so this gradient has to be much larger. If this gradient is much larger than this one, then the velocity here has to be faster. And therefore, on flow on this streamline, you could rationalize it must arrive, it must have a shorter transit time to get from upstream to downstream than does this one. And this one must be faster than this one. And this one must be faster than the one that goes here. And this one must be faster than the one that goes here. Whoops. And out here. And back in here. Well, I guess it's this one actually, isn't it? And it has to be much faster than this one, which goes out here, travels the universe to infinity, and comes back here, which is infinitely long in terms of half space. And so the net effect of that is that anything that's carried by this streamline will arrive earliest. And so the contaminant loading from this, it's actually a bit like your Yucca Mountain calculation for the parallel stream tubes going from Yucca Mountain to Longstreet. This will be the fast-flowing one. This will be the next one, which is slower flowing. And the third one would be this one. You only had 3, I think, in your particular case. And so the point is that you'll get dispersion, which if you looked at the arrival, the residence time distribution, without going through the equations again, is that would be an arrival here. So if it was plug flow, even if it was plug flow, then the arrival would look like this. This would be flat. This would be C over C0 is equal to 1. And the reason that it would be true for plug flow is that you can imagine, I'm not sure if I can draw it. Well, I suppose it would be this, right? So this would be the, if this were, I guess it's time, yeah. If this is concentration versus time. This first stream tube would arrive at some time. And the residence time distribution would look like this. Because it comes in at some concentration, arrives here. Once it's arrived at that concentration with plug flow, it will always keep on making that concentration. The next stream tube arrives a bit later. It will also have a component of concentration. And it will keep on at that forever, so long as you keep the concentration here. The next one will be this one, which will arrive later. And so you basically end up building up this residence time distribution as a function of time. These different, more external stream tubes have later and later arrival times. And so you can imagine that if you put that little histogram of these arrivals together as a continuous distribution, it's going to look like this. And so even in the case that your longitudinal dispersion is 0, right, plug flow, absolutely no dispersion, your experiment tells you that it has some. And it tells you have some because the experiment itself introduces this kind of dispersive flow field. And so it's not very useful to do that. And so of all the methods we've talked about so far, doing laboratory experiments, no good, too small a sample, and it doesn't really include the physics of how this occurs with dispersion at larger scales. And we've looked at 2 different field methods of doing it, and they don't work so well. They satisfy the requirement that it can look at a really big volume, a representative volume, but they fall down on the fact that, I guess mainly the fact that both of them introduce this artificial dispersion into it. It's quite apparent, I think, in this 2-well case, but it's also kind of apparent in the single well case, because you think about it, if you look at flow within a single well, it's actually not so. Then it has to flow in this. So this is the stream tube that is flowing out from the well to get to the exterior. So if you look at the velocities as you went out from this particular well bore, what would the advective velocities look like as you go laterally outwards? I'm getting a cramp in my finger. It's going to be, for a given velocity here, it's going to be some magnitude. Once it flows out here, you have the same velocity, which is equal to a volumetric flow rate divided by a cross-sectional area. The cross-sectional area is getting bigger here, to here, to here. And so the velocity that starts out close to the well must drop as it goes outwards. And so, bless you. So as you physically go out here, it starts off at a big velocity here, and there it ends up at a smaller velocity here. So when you pump it out, it has different velocities all the way it goes out. Suck it back in, it has different velocities as it comes in, and you get mixing at different rates as a function of that. And so it jumbles up, it complicates the analysis because you can't really take account of that. It's much more apparent in this 2-well test because it's geometrically, it's really, you could think of it as the same velocity all along this stream tube, which is fast, same velocity all the way along this stream tube, which is slower, same velocity all the way along the stream tube, which is even slower. It's not going to be the same, but it's easier to think of it that way. So we're kind of 0 for 2 or 0 for 3, right, in terms of being able to do this usefully. And so what are we going to do? So the other way we could do it is the third way. And it really relates to the last method that we talked about being under natural gradients, so-called natural gradient experiments. And so that means that you don't do anything other than just put the stuff in the ground, lay it there if you like. You don't actively pump it in. You let it be carried around by the gradient that exists there. So like the landfill where we had some gradient of head underneath the landfill, that's the natural gradient that's in place. And so the stuff that drops out of the landfill by diffusion gets advected at that natural gradient. And it has a couple of two advantages that satisfy the 2 drawbacks of the other one. One is we hope to do it on a big volume by looking at it over a long period of time. And 2, we want to be able to do it at a velocity which is pretty much reflective of the true velocity that occurs in the system. And so this is one experiment from Canadian Forces Base Borden in northern southwestern Ontario. Ontario is a huge province, so it's 3 hours north of Toronto, something of that order. Happens to be a Canadian Air Force base where there's a sand aquifer which overlays clay aquiclude or aquitard, so that anything you put into this upper sand aquifer doesn't get into the deeper reaches and the aquifers below that. It's sand, and so you can actually excavate in this very easily. And what this is a profile of an experiment that was run a number of years ago now to put contaminant in place at this point here, at time t0, and then look how it looks after 1 day, how it looks after 85 days, I think, what it looks like after 462 days. These are just contour plots of the plume. and what it looks like after almost 2 years. And it's not very easy to do everywhere. You could imagine that if you did it here in the limestone, then to be able to get a picture of what these contours look like, you'd have to pepper it with holes. As if you've looked any further in the Smithville assignments, you'll see that there's some plume distributions, concentration distributions, and the dots on those are maybe 100 or more boreholes put in place just to be able to pierce the plume and drilled in rock. But this is a shallow aquifer where you can basically put a steel, 1/10 of an inch diameter capillary tube physically into the ground and suck some water out of it to be able to get a concentration that then you put in a GC to be able to measure the relative concentration, or ICP-MS, to be able to measure concentrations, and then you plot those. And so what can we do with that? Well, you want to be able to analyze those to be able to figure out exactly what the dispersion characteristics are. And so you would note somewhat of a similarity between what's going on here in this example, where we said that if you introduce it at time 0 and look at it sometime in the future, then you can use this Gaussian distribution to say something about the size of the plume. We know that it will have spread to 3 times the standard deviation of this distribution, and it will contain, this is 99.7% of the mass is contained within this. So if you find the outer rim, if you like, of the plume, then that's the length you need. If you know the length is a certain 50 meters, then you have a way of being able to calculate. If you know when it occurs, you can calculate what this dispersion is. And so that's really all we're doing. This 3 here, by the way, is 3 times the square root, not the cube root of that, which you can tell from the dimensions. Wouldn't be the right dimensions if it wasn't. And so this is the basic idea. So what do we need to get? What can we get from this? We know that it's traveled 9.5 meters in 83 days. Velocity is equal to length over time. So this is equal to 9.5 meters over 83 days, whatever that is in seconds or otherwise. And you can use that to be able to get an advective velocity. So the advective velocity is something of the order of 1/10 of a meter per day. So quite fast. It's quite free-flowing, very small gradient, but quite high permeability, high conductivity materials. We know that for each of these plumes, that we can get the statistics from, what am I calling it? This would be this would be the length longitudinally. This would be the length transversely. You can measure it right from this. Equiaxed here, much longer and skinnier here, showing that over time advection is allowing it to expand, which is interesting. And so this is dispersivity in the longitudinal direction, I'm guessing. So at 85 days, I'm guessing that this is this is longitudinal, so this is longitudinal. So I'm not going to measure this off, but I'm guessing this is, it's the half length. That's what I was thinking it was on, right? So this is 2L2, and this is 2LT. And so this length here, to me, looks like it's about the same as this. This is about 10 meters. If this is 10 meters, then the actual length is 5. We know it took 85 days to get there. This is in days. And so from this expression here, we know that this here is 5 meters. We know that this is 85 days. And just by rearranging it, we end up with the dispersivity. And it turns out to be 1/100th of a meter squared per day, or almost 2/100ths. If we do it for this one, where I guess if this is 10 meters, 10 meters, 20 meters, this looks like it's about 30 meters. Not quite, yeah, okay, 28 I guess. I actually measured it, I suppose. 28 meters, same deal. You end up with these numbers. So we actually have a magnitude for the longitudinal dispersivity. So this would be dl, and that would be equal to alpha L times the advective velocity plus the diffusion coefficient. Whoops, no. And so we said that the biggest we think this might be is of the order of 10 to the minus 9 meters squared per second. How big is that? I'm guessing it's small, but I don't know. I guess we could check that. This term overall here is coming out to be 0.1 10 to the minus 1 meters per day. So is that bigger than this? I'm not sure. So a day is basically 10 to the 5 seconds. So 1 day equals, what is it, 86,700 seconds. Remember this, sometimes I can't remember how to get home at night, but I can remember this. I think it's so, 10 to the, which is about 10 to the 5 seconds. And so 10 to the 5 seconds would be, I guess, 10 to the minus 4 meters squared per day. 10 to the minus 4. It didn't come out very well. So this number here is 10 to the minus 4. This number here is 10 to the minus 1 meters squared per day. And so to get there, this number has to be big, right? It can't be small. And so these two numbers have to be roughly the same order as each other, in which case we can throw this away. This is the biggest, and this is the biggest it can be. It could be smaller than this because it weaves in itself out. We said we could reduce this by a factor of 100. And so what we've done is we've been able to calculate what this is from our field results. These are just this number here. And if we know what this is, and we know what advective velocity is from here, then we immediately know how to get this value here, which is a physical property of our aquifer. And I don't know if I calculated on here. I don't, and I'm not going to. But yeah, I do, I guess. So, right? So that's the interest. We'd like to have some parameter that represents our aquifer. We can measure it if we take some characteristics of what the plume looks like at different snapshots in time by looking just at the length of this, how much it's spread as a function of how long it's take to get there, and what its advective velocity is. We can define a number which is d sub L, which is useful to us, but it's much more useful to us if we can make it into an invariant parameter, which is really a function of the aquifer and not conditioned by whatever the velocity is that the flow is occurring, because it could be occurring at a larger flow rate in some different place in the aquifer. So we like to get this value of alpha sub L, and we can from this just by doing this. We have everything we need to calculate alpha L. And it seems to me that if we do that, this is the calculation. So I guess this is a value of alpha L. So I don't know if I've done it here. I don't see that I've done it here. No. Okay, so that's different. Let's wait for the punchline on that. So we can get a value of this dispersion coefficient. If we take the width of the plume, so we see that it spreads longer along the direction of flow. So this is the direction of flow, obviously, here. This length here is longer than this width here. And so you'd expect that the longitudinal dispersivity is going to be larger than the transverse dispersivity if we then use these widths. And this is the calculation for this, and this is the transverse dispersivity. And so this is 0.02, this is 0.001. So this is about a 20th, right? Is that right, of that? Should find out. 0.01, no, maybe not. So this is almost 0.01, and this is almost 0.02. Yes, they should be a factor of 3 different. So they're a factor of 2 different, which is fine. So this is about half of these magnitudes. And so the fact that it's a half of these it means that it spreads out longer in this direction than it does the width. And that's because the magnitude of this dispersion in the direction of flow occurring accentuates this longitudinal dispersion of the system as a function of behavior. And so we could, if we wanted to calculate the value of alpha L, I don't know if I'm able to do that. I suppose I could. I don't have a good track record recently. What would the calculation be? Alpha L would be equal to this measured dispersivity divided by the advective velocity, which is what? 2 times 10 to the minus 2, is that right? Meters squared per day. And the advective velocity was something like 10 to the minus 1 meters per day. Yeah, and so the units come out to be length, which would be 10 to the 1. What's that? 2 times 10 to the 1? Minus 1, right? So 2 times 10 to the minus 1, so 0.2 meters. And so some ballpark magnitude of this is roughly 0.2 of a meter. And if you look at this in terms of the scale of the measurement, we'll come back to this, there's some suggestions that maybe you can take how far the plume has gone, or how big the plume is, which in this case is 61 meters, and the value of this alpha L, which seems strange, should be equal to this length traveled divided by 10. So in our case, it's 61 meters, and if you divide 61 meters by 10, you end up with 6 meters, which isn't quite the same as what we have here. And that's what this calculation is going on here. But why should that be? So we've satisfied the case then. I'm going to zoom out on this so we can look at the whole thing together. So we've said that lab experiments are no good, too small a sample, doesn't represent the heterogeneity at field scale. Force gradient tests sample big scale processes, but they do it at large velocities and gradients that are much higher and velocities much higher than are happening in reality in the real world when you're looking at these behaviors. So they don't work so well. So we'd like to use natural gradient experiments if we can, because they satisfy both those requirements. Big sample and a natural flow field that isn't messed up. And so we can get values for this aquifer-dependent parameter, which is dispersion coefficient alpha L, which is in units of meters. And we've gone to some lengths to do that, and we think we can get it out of here, and it comes out to be 0.2 of a meter. And that's great. So we can use that. So now you can use that. So if you, instead of having data only up to 462 days for your plume that looks like here, if you have the value of alpha L for this, and you know what the velocity, advective velocity is, you should be able to predict that in another 200 days, this is 600 and some days, that the center of mass of that plume would be here, because the advection has gone from this location to here, and that it should have spread out some more, because we could calculate exactly what this 2 times the length of the plume would be at that time. So we've been able to make a prediction. So we think we should be happy with ourselves that we've solved that problem, and now we can make a projection. It turns out that that's actually not quite true. And the reason it's not quite true is because observations are like this. And so if you could imagine, this is in Feder's book also, if you could imagine going around the world to a whole bunch of places where you could go in situ, and you know the time that something was spilled, and you know now that you're measuring it what the plume looks like, So you could do exactly what we've just done with the Borden plume to these 100 different plumes. If you do that, then for every single plume, you could measure, from the size of the plume, you could calculate what this dispersion coefficient alpha L would be. And you could also measure how big the plume was itself. This term here, the length of the plume. Actually, the two parameters that describe this, right? So this is the length of the plume, right here, if you like. And alpha L would be the number that you applied to be able to get from that. And it turns out that they plot, this is a shotgun blast of the plots. So this is one plume, this is another plume, this is another plume, could be anywhere around the world. And so there's no discussion here of whether it's a clay or a shale or a gravel or a sand, but there seems to be some relationship that's completely independent of the hydrological properties per se, that follows, well, these are the bounding values. This is the upper envelope. This is a lower envelope. And this is just a line, a best fit line that you could imagine might go through these. The equation of this best fit line is, I'll just write it out, is L over 10. And so this is the length of the plume. And this is just 10. This is the equation of this line. And it has dimensions. This is a length dimension. This has units of length as well, this longitudinal dispersivity. And so the reason that we looked at a value of 1 over 10 on that previous slide was because the actual field data, if you look at them, completely independent of any kind of hydrogeological properties, you could get an estimate of what this value is just by doing that. You could make the argument that if you have a plume that's 100 meters long, then you'd think that the dispersion magnitude would be this, but the range of values actually aren't particularly well constrained, because this is 2 orders of magnitude here, and this is 1.5 orders of magnitude here, say 1. And so this together is over a range of 3 orders of magnitude. So it's not particularly well constrained, but there's some pattern there. And so the question is, why would it be that this general relationship is that if a plume is very short, then its dispersion coefficient is small, and it's very big, then it's much larger. And the rationale for that, if you can imagine, is really due to what we think dispersion is. So what we think dispersion is the opportunity to be able to pick out these kind of superconductors that would have faster flow velocities, and therefore the fingers get accentuated because they get carried down these fast flow paths, and they get further and further ahead of the main plume as you go downstream, so there's much more spreading. And so the rationale, I think, is this. If you look at, it's actually based on ideas of fractals, but so the idea is that if you look at an aquifer, and if you look at the heterogeneity that you might have in that, the really big features that have really high velocities on them would be things like faults, where you've had fracturing and displacement that now have very high permeabilities. And these faults would be of large scale and have high permeabilities. There'd also be fractures at smaller scale, which would also have kind of enlarged permeabilities, but they'd be much smaller. And so the idea is, I think, if you have a plume that develops, if it's only a very small plume, which L is relatively small, then it doesn't really see these big features, but it sees some little features which might be little fast conductors, which would allow it to kind of spread out in microcosm. As it spreads out in microcosm and gets even slightly bigger, then all of a sudden, as the length scale is this, then now it sees this big feature here, and it sees this big feature here. And so it now gets to sample those. So the idea is that when it's small, it really only sees the variability, which is in a small core sample, which isn't very much. As it gets progressively larger, it now samples a bigger and bigger region. In that bigger region, there's a better chance that one of these big superconductors is there, and therefore it can be zipped along this. As it gets even larger, then maybe it sees a superconductor that it sees and then goes on. So that's basically the idea. And so the rationale for this plot, which may be deflating to us, right? Because we said we can't use core tests, we can't use field tests under force gradient very well, but we can use natural gradient experiments. I guess it comes down to the fact that maybe we don't need to, because immediately, if we have this expression, we can get some idea of what the dispersion characteristics might be just by looking at it. And if you look at this also, if we want to look at transverse dispersivity, then that might be of the order of a third of the value of this longitudinal one. So remember these things like ellipses, when you look down on them, they look like ellipses because they spread out more longitudinally than transversely. And so not unreasonably, you'd expect this to be smaller than this, and this might not be about. Could be a half, could be a third, could be all kinds of numbers given this spread here, but it gives us a way of being able to do that. And so that allows us to be able to say something about how plumes will spread as a function of time. And so if you like, it all comes down to this cameo or cartoon of this, is if we know what the behavior is at some current time, say, if we know this, then we could immediately go and we could use alpha L is equal to length over 10. We have the length here, and so we can calculate this. If we know this, then we can certainly calculate what this would be. From this expression. So we have this. If we know what the advective velocity is from Darcy's law, we know advective velocity is equal to hydraulic conductivity, porosity, and gradient. Things you could measure from an array of wells. It was the one question question 2 on maybe your second assignment that you didn't do that was going to get you to do this. But if you have a gradient and you know hydraulic conductivity and a porosity, you can calculate an advective velocity. So you could calculate an arrival time. So you can get this. And we have some ideas of this, right? Of the order of 10 to the minus 9 meters squared per second. And so if we know what this is, then you have everything you need to be able to calculate what it would look like in 2 years later, right? Just from doing this, from using this the expression here. And so that's what we're trying to do. We'd like to be able to, from current measurements, current observations, be able to say something about what it might look like sometime down the road. And ultimately, we'd also like to say, if we stick a straw in here and suck water out at 1 year after this, whether we'd actually stop this from happening by capturing all the stuff in this well as we pump and treat it, just a dissolved component. And so that's really all we wanted to do. So everything we've talked about has up to this point been framed in terms of what we referred to as conservative transport. And so what we'll talk about next time is in terms of what happens now if the stuff that ends up in the aqueous phase doesn't all stay in the aqueous phase but gets sorbed onto the material that it flows through. Sometimes that's good, because you can imagine if you take some out of the flow field and put it on the solid, then it has to arrive in a concentration that's much lower downstream, and you think that would be good. The negative, I suppose, would be that if you have it arrive downstream and then you clean the aquifer downstream, but it's all sorbed upstream, then any clean water that flows through the upstream portion will desorb the stuff that's on the grains and re-entrain it into the water, the aqueous component, and then it will arrive downstream at the other place. And so good or bad, I guess, is in the eye of the beholder. So anyway, so I'll leave it there. Thank you very much.